In this lecture, we will discuss Cauchy-Goursat theorem for multiply connected domains. In the last lecture, we have discussed the Cauchy-Goursat theorem for simply connected domains. That was for a simply connected domain, if f of z is analytic inside or analytic in the simply connected domain, then for any simple closed contour C, in D, we have integral over C f of z dz is equal to 0. That was the Cauchy-Goursat theorem for simply connected domain. Now, here we are going to discuss the Cauchy-Goursat theorem for multiply connected domain. Suppose first we can take a doubly connected domain. A doubly connected domain. Let this D be a doubly connected domain. So we have to exclude one portion, that is one hole. A doubly connected domain is actually a domain with the one hole. Okay, so this will be the portion of the doubly connected domain. Okay, so if you are in this doubly connected domain, we cannot conclude that for a simple closed contour C, we cannot conclude that integral over C f of z dz is equal to 0. We cannot conclude this because if you are taking a contour, a simple closed contour like this, okay, if this is C, then actually here we are given that f of z is analytic inside or in D. That means it is analytic here in this region. So it may not be analytic in this region. Okay, in this region it may not be analytic. Okay, so in that case we cannot conclude f of z dz integral over c f of z dz is equal to 0 because in this here may be points at which f of z is not analytic. Okay, so we cannot conclude this. So in such a case, if suppose I am drawing two simple closed contours, one is this C. I'm drawing a C like this. This is C. Okay, so this is the orientation of C, and I am drawing one more simple closed contour. This. Okay, let it be C1. This closed contour is C1. Now we know f of z is analytic in this region, but it may not be analytic in this region because we are given that f of z is analytic in the doubly connected domain D. In the doubly connected domain D, that means f of z is analytic in the region lies between these two yellow lines, yellow curves. Okay, that is this is the region. Okay, this is the region D. So suppose we are given f of z is analytic in D, then we can f of z may not be analytic the point at which inside this region, right? So now if you are taking two simple closed curves, one is C and the other is C1, and this C1 is directly I mean enclosed, or it is we are drawn on the boundary of uh, this hole. Okay, so now I'm considering a new path, or suppose we are introducing a cut AB like this. A cut AB, then I'm introducing a new path. This is actually from A to, this is passed through this this is the way, and entering to here, and then come to this, then it goes to like this, then reached here. That means this is actually C. Okay, C union, then AB, the line AB, then this is negative C actually. This is C actually, but the orientation is negative. Okay, so see, this is C1. Okay, C1, but the orientation is negative. So the integral will be negative on that. Union, then B to A, that is BA. Okay, so that is C union AB union BA union C1. So we will get in that case, what about the, so our region is actually I am taking the this course contour is like this, it's like, and taken here, then like this. So the interior part of this some closed this contour capital C is actually, the interior part of this contour is actually, this is coming like this, and through this, and from here like this, then this way, and reach back here. Okay, so the interior portion of this new contour is actually this. This will be the interior contour. Okay, now we can say that uh, in this, on this new contour, f of z is analytic. Also f of z is analytic at any point inside this contour. Okay, so we have the integral of this along this new curve is actually integral over c f of z dz plus integral over ab f of z dz plus integral over this. This is actually minus, right? Minus integral over c1 f of z dz plus integral over ba f of z dz is equal to 0 by now this is a simple closed contour actually. So by simply connect the Cauchy-Goursat theorem for simply connected region, this will be equal to 0. Okay, because now we are taken this is the region only, so in that region and on this curve f of z is analytic. Okay, so we have by Cauchy-Goursat theorem this is equal to 0. So from this we know this is integral a to b f of z dz, and this is integral ba f of z dz. So this is the negative of this. So integral ab f of z dz is equal to negative of integral ba f of z dz. So this is equal to, we can write integral over c f of z dz plus integral ab f of z dz minus integral over c1 f of z dz. Here is, can be written as integral ab minus ab or a to b f of z dz is equal to 0. So this is cancelled, and this is equal to integral over c f of z dz is equal to integral over c1 f of z dz. Okay, that means the integral over this c1 or integral over c f of z dz is equal to integral over c1 f of z dz. Okay, this is sometimes called the principle of deformation of contours. Sometimes this result is called the principle of deformation of contours. So this result gives us, if we are given that f of z is analytic in a doubly connected domain, f of z is analytic in a doubly connected domain, this, that means f of z is analytic in this region only. Okay, that means there may be any point in this inside this region at which f of z is not analytic. Okay, if you are given that f of z is analytic in this region or in a doubly connected domain D, then integral over C, if this is C, integral over C f of z dz is equal to integral over C1 f of z C1 dz, where C1 surrounds this portion, this whole. Okay, so uh, the integral of f of z over C is equal to the integral of f of z over C1. That is, these both this integral have the same values. Okay, so the benefit of this principle of deformation of contours is actually, if we want to evaluate an integral over a complicated simply closed contour C, we can replace this simple closed contour C with a new simple closed contour which is more convenient. Okay, that is, if we want to integrate this f of z with over this in the over this simple closed contour C, we can replace this C by a convenient C1, a convenient curve, simple closed curve C1. Okay, to evaluate the integral. That is the benefit of this principle of deformation of contours. Okay, now we can discuss an example. Evaluate integral over C dz by z minus I, where C is the contour given in this figure. Okay, so we have to integrate this 1 by z minus I with over the contour C, where C is this. Okay, so here actually our f of z is this, f of z is equal to 1 by z minus I. We know this function is analytic everywhere in the complex plane except at the point z such that z minus I is not equal to 0, right? Therefore, f of z is analytic everywhere except at z such that denominator is equal to 0. That is, z is equal to I. So, f of z is not analytic at z equal to I. That is, the I is this point. Okay, so f of z is not analytic at the point I, and it is analytic everywhere in the complex plane except at this point z equal to I. So we have to integrate this function f of z is equal to 1 by z minus I along this curve C, along this closed curve C. So here f of z is equal to 1 by z minus I is not analytic at only at the point z is equal to I. This is the point I. Okay, and it is analytic everywhere in this inside this C and on C. Okay, so we can we have to integrate over this C, so we can take a more convenient simple closed curve. So if we can take for simply we can take a circle with the center I and radius 1. This is 1, this is minus 1, this is 1. So we can take this a circle with the center I and the radius 1. That means mod z minus I is equal to 1. This is actually a circle with the center I and radius 1. So it will be like this. So I am taken a circle with center I and radius 1. Okay, let this be C1. Now that is, I have taken C1 as this mod z minus I equal to 1. Okay, that is with the center I and radius 1. So by the principle of deformation contour, deformation of contour, we have integral over C f of z is 1 minus 1 by z minus I dz is equal to integral over c1 1 by z minus I dz, where c1 is this. Okay, where c1 is this. So now we can directly integrate this, because it is convenient to integrate the over c. It is better to integrate over c1, because c1 is a circle with the center I and radius 1. Okay, where c1 is mod z minus I equal to 1. Now on c1 we have z minus I is equal to e power it for 0 less than or equal to 2 t less than 2 pi. That is, therefore z dash of t is equal to, differentiating with respect to t, we have z dash of t minus equal to I into e power it. Okay, so therefore this is equal to integral over c1. We know this is f of z of t into z dash of t dt. Okay, so this is equal to integral t from 0 to 2 pi. F of z of t is actually 1 by z minus I. So 1 by z minus I is nothing but z minus I is e power it. So 1 by e power it into z dash of t. Z dash of t is I e power it into dt. Okay, so this is nothing but I into integral 0 to 2 pi dt, which is equal to I into t from 0 to 2 pi, that is nothing but I into 2 pi, that is 2 pi I. Now we can generalize this result, that is, suppose z naught is any constant complex number interior to any simple closed contour C, then we have integral over C dz divided by z minus z naught power n is equal to 2 pi I if n equal to 1 and 0 for n is an integer not equal to 1. Okay, if n is an integer and if n equal to 1, then this integral will be dz by integral of over c dz by z minus z naught power n is 2 pi I, and it is 0 if n is not equal to 1. N is an integer which is not equal to 1, then the integral is equal to 0. Okay, so we can generalize this. So how to prove this? Okay, to prove this, we already proved the case when n equal to 1, and here we are taken z naught as I. Okay, so here we are given that z naught is a constant interior to any simple closed curve C. Okay, z naught is a constant interior to any simple closed curve C. Let this be C and this point be z naught. Okay, now if n equal to 1, if n equal to 1, we have we have to find the integral dz by z minus z naught power 1. Okay, so as in the previous case, we can say that here f of z is actually f of z is equal to 1 by z minus z naught, and it is not analytic only at the point z naught. Okay, so we can take, we can by the deformation principle, a principle of deformation of contours, we can take a curve, another curve c1 here. Okay, and it can be taken as the circle with the center z0 and radius 1. That means we can take, that is, choose c1 such that mod z minus z0 is equal to 1. that is circle with the center z0 and radius 1. Okay, therefore by deformation principle or principle of deformation of contours, principle of deformation of contour, we have integral over c dz by z minus z0 is equal to integral over c1 dz by z minus z0, where c1 is this. So we know on c1 we have z minus z0 is equal to uh, e power I t for t varies from 0 to 2 pi. Okay, therefore dz by or z dash of t, z dash of t is nothing but z dash of t is actually differentiating with respect to t. We have z dash of t minus 0 equal to I into e power t. So we have this integral is nothing but integral from 0 to 2 pi, t from 0 to 2 pi, f of z. F of z is 1 by z minus z naught, which is nothing but z minus z naught is e power it. So 1 by e power it into z dash of t. Z dash of t is I e power it into into dt. Okay, so we already have this as in the case of this problem. Okay, we have integral over c f of z of t into z dash of t. Okay, so we have this is equal to I into integral 0 to 2 pi into dt. This is equal to 2 pi I. So we have proved uh, for n equal to 1, if n equal to 1, we have proved in this integral is equal to 2 pi I. Now we have to show that if n is not equal to 1, we have to show that this integral is equal to 0. Now suppose we are taking n equals 0. If n equals 0 or n is negative. Okay, now next case is this is we can take this as case 1. Okay, now case 2, if n is less than or equal to 0, n is an integer uh, which is 0 or negative. Okay, where n is an integer. Okay, so if n is less than or equal to 0, then our f of z is nothing but 1 by z minus z naught power n. If n equals 0, it is actually 1 by z minus z naught power 0, that is 1, which is a polynomial. If n is less than 0, for example, if n is less than minus 3, if n is minus 3, then f of z is equal to 1 by z minus z naught power minus 3, which is equal to z minus z naught power 3. Okay, it is a polynomial. Okay, so if n is less than or equal to 0 and where n is an integer, then we have f of z is equal to 1 by z minus z naught power n is which is a polynomial, which is a polynomial. Okay, so therefore f of z is entire function that is analytic everywhere in the complex plane. So by Cauchy-Goursat theorem, therefore by Cauchy-Goursat theorem, we have f of z is analytic everywhere in the complex plane. So integral over c f of z dz, that is equal to integral over c 1 by z minus z naught power n dz is equal to 0 by Cauchy-Goursat theorem. So we have proved if n is less than or equal to 0, then it is integral is 0. Now we need to prove that case 3. Okay, if n is greater than or equal to 2, we already chosen n equal to 1 and n is less than or equal to 0. Now we have to prove that if n is greater than or equal to 1, that is if n is positive which is not equal to 1, then we have to show that this integral is 0. Okay, so here also we can use the Cauchy deformation deformation of contour, principle of deformation of contour. Here our f of z is actually uh, 1 by z minus z naught power n. Clear? So here also we can use this. So here also it is not analytic only at the point z is equal to z0. Okay, it is analytic everywhere in the compressed plane except at the point z equal to z0. So as in the previous case, let this be our C and this is the point z0. We can take a circle with the center z0 and radius 1. Okay, that is choose C1 as mod z minus z0 equal to 1. That is, this is C1. Okay, so on C1 we have uh, mod z minus z0 is equal to 1. Therefore we have z minus z0 is equal to e power it for 0 less than or equal to t less than or equal to 2 pi. Okay, therefore differentiating with respect to t, we have z dash of t minus 0 equal to I e power it. Okay, now therefore we have the integral is nothing but integral over c f of z dz is nothing but we have integral over uh, over c f of z of t into z dash of t dt. So here f of z is actually this, so this is equal to integral over c uh, 1 by z minus z naught power n into z dash of t dt. So here we know z minus z naught is actually e power it. So this is 1 by e power it power n into z dash t I e power it into dt. For t varies from 0 to 2 pi. Okay, so this is nothing but integral 0 to 2 pi I can be taken outside e power 1 minus n into I t dt. So on integration we have here I into e power 1 minus n into I t divided by 1 minus n into I from t from 0 to 2 pi. Okay, so this is equal to, we can divide this I and it will be 1 by 1 minus n into replacing this we have e power I into 2 into 1 minus n pi minus e power 0. Okay, so this is nothing but 1 by 1 minus n into e power this e power I into 2 1 minus n pi is nothing but cos of 2 into 1 minus n pi minus plus I into sine of 2 into 1 minus n pi minus here e power 0 is 1. Okay, now we know that this is 1 by 1 minus n into cos 2 into 1 minus n pi is actually cos we know cos 2 pi or 2n pi is 1. Here it is uh, even 2 into 1 minus n is an even number, so cos 2 into 1 minus n pi is 1 plus I into sine 2 1 minus n pi is 0 minus 1. This is equal to 0. Okay, this is equal to 0 because 1 is not equal to n. Okay, since n is not equal to 1, we have n is not equal to 1 implies 1 minus n is not equal to 0. So this is equal to, this is a non-zero number. So this integral is equal to 0 when n is uh, greater than or equal to 2, where n is an integer. Okay, so we can conclude that this, if n is equal to 1, then this integral is equal to 2 pi I, and if n is an integer which is not equal to 1, then this integral is equal to 0. Okay,